Tonight, we're going to explore one of the strangest possibilities in modern astronomy. Earth may not be the rare kind of world we once imagined. There may be thousands of worlds already known that share pieces of Earth's story. And far beyond those, there may be billions more hiding in the dark, orbiting stars we have barely begun to study. By the end of tonight, you're going to understand why that possibility is so unsettling. Because if Earth-like worlds are common, then the universe should feel a little less empty. Life should feel a little less isolated. The silence around us should feel easier to explain. Yet the deeper we search, the stranger that silence becomes. As of May 21st, 2026, NASA's Exoplanet Archive listed 6,291 confirmed planets beyond our solar system. 6,291 worlds. Some are giant planets larger than Jupiter. Some orbit so close to their stars that their skies would glow with unbearable heat. Some are frozen in distant darkness. Some are strange worlds larger than Earth but smaller than Neptune, a kind of planet our own solar system does not even have. But hidden among those thousands are planets that make the search feel different. Worlds close to Earth's size. Worlds orbiting inside the habitable zone. Worlds receiving the kind of starlight that could, under the right conditions, allow liquid water to exist on the surface. And that is where the mystery begins. Because once you find one possible Earth, it feels like hope. Once you find thousands of planets and realize many more are waiting beyond the limits of our instruments, it becomes something heavier. A pattern, a question, a quiet pressure building behind every measurement. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Most stars are now believed to have planets. Many stars likely have several. And our galaxy is only one galaxy among trillions in the observable universe. Given those numbers, Earth should feel less alone. There should be other blue worlds, other rocky surfaces under pale skies, other atmospheres holding heat, other oceans reflecting starlight, maybe even other living planets carrying their own forests, storms, microbes, animals, or civilizations. But so far, we have found only one confirmed living world. This one, Earth. We have catalogued thousands of planets. We have measured shadows crossing distant stars. We have watched stars wobble under the pull of hidden worlds. We have begun reading atmospheres from tiny traces of light. And still, no second Earth has answered back. No confirmed biosphere. No clear alien forest. No unmistakable living atmosphere. No signal from a civilization looking up from its own version of home. That is the contradiction at the heart of tonight's journey. The universe appears to have no shortage of planets. It may have no shortage of rocky worlds. It may even have no shortage of planets sitting at the right distance from their stars. Yet life, at least from where we stand, remains known from a single example. One planet, one atmosphere, one ocean-covered world where chemistry somehow became cells. Cells became animals, and animals eventually built telescopes to search for company. So tonight, we are going to move carefully through that mystery. We are going to begin with the first confirmed planet around a sun-like star. Then we will follow the telescope that turned planet hunting into statistics. We will look at what the habitable zone really means. Why Earth-size does not automatically mean Earth-like. why red dwarf stars may create some of the most promising and most dangerous possible Earths, and why atmospheres, water, and biosignatures are far harder to interpret than the headlines make them sound. If you enjoy calm journeys through the stranger parts of space, take a moment to like the video and subscribe. It helps this channel reach more curious viewers who love exploring the universe slowly, quietly, and deeply. Now let's continue. Because before we can understand why possible Earths are so unsettling, we need to go back to the moment humanity found its first confirmed planet around another sun. That first confirmed planet around another sun-like star was announced in 1995. The star was called 51 Pegasi. It sits about 51 light-years from Earth, in the constellation Pegasus. From our sky, it looks ordinary. A faint yellow-white star, similar enough to the Sun that, for a long time, no one would have looked at it and expected a revolution. Then two Swiss astronomers, Michel Mayor and Didier Queloz, noticed something unusual. They were using a spectrograph at the Haute-Provence Observatory in southern France. A spectrograph is an instrument that spreads starlight into its separate colors, almost like a prism, so scientists can measure tiny shifts in the light. Those shifts revealed that 51 Pegasi was wobbling. The star was moving slightly toward Earth, then slightly away from Earth, again and again, in a steady rhythm. The movement was extremely small. The star itself was enormous, but its motion was being tugged by something orbiting nearby. That hidden object was a planet. It became known as 51 Pegasi b. Later, it was also given the name Dimidium. The discovery was so important that Mayor and Queloz later shared the 2019 Nobel Prize in Physics for opening a new era in astronomy. For the first time, humanity had confirmed a planet orbiting a star like the Sun. The universe had changed. A star that once looked like a lonely point of light now had a world moving around it. But the world itself was strange. 51 Pegasi b was nothing like the gentle Earth twin people might have imagined. It was a gas giant, roughly in the same broad family as Jupiter. A huge planet made mostly of hydrogen and helium, with no solid surface where oceans or forests could rest. And it was orbiting incredibly close to its star. Jupiter takes almost 12 Earth years to travel once around the Sun. 51 Pegasi b takes only about 4 days. Its year is shorter than a normal week on Earth. That single fact made the planet deeply confusing. In our solar system, the giant planets live far from the Sun. Jupiter, Saturn, Uranus, and Neptune all orbit in the cold outer regions, where ice and gas were easier to gather during planetary formation. That pattern made sense. Large gas giants seemed like they belonged far from their stars. Yet 51 Pegasi b was sitting extremely close to its star, heated intensely from above, rushing around in a tight orbit. Astronomers began calling worlds like this hot Jupiters. They are giant planets with short orbits and extremely high temperatures. Many are so close to their stars that their upper atmospheres can be blasted by radiation and stretched by stellar gravity. Some may have winds moving at thousands of miles per hour, carrying heat from the day side toward the night side. The discovery forced scientists to rethink how planetary systems form. A planet like 51 Pegasi b probably formed farther out, where a gas giant could gather material more easily. Then, through gravitational interactions with the disk of gas around the young star, or with other planets, it likely migrated inward. Migration means the planet changed its orbit over time. It slowly moved from one region of the system to another. That idea mattered because it showed that solar systems are not always calm, fixed arrangements. Planets can shift. Giant worlds can move. Early planetary systems can be messy places filled with collisions, tugging, scattering, and rearrangement. So the first confirmed planet around a sun-like star gave scientists two discoveries at once. Planets existed around other stars, and those planets could live in arrangements our own solar system had never shown us. This also shaped the early years of exoplanet hunting. Large planets close to their stars are easier to find. They tug harder on their stars. They complete orbits quickly. Their signals repeat in days instead of years. A small rocky planet like Earth creates a much weaker wobble. Earth also takes one full year to circle the Sun, so scientists need much more time to confirm the pattern. That meant the first discoveries were biased towards strange, massive, close-in worlds. Astronomy was finding the easiest planets first. The galaxy was opening, but through a narrow doorway. 51 Pegasi b proved the doorway was real. It showed that stars like the Sun could have planets. It showed that our solar system was only one possible design among many. But one strange giant planet could not tell scientists how common Earth-sized worlds were. For that, they needed a different kind of search. A search that could watch many stars at once. A search built to turn planet hunting into a census. That census began with a telescope built to stare. On March 7th, 2009, NASA launched the Kepler Space Telescope from Cape Canaveral, Florida, on a Delta II rocket. Its mission was quiet in concept. Kepler would look at one fixed patch of sky, near the constellations Cygnus and Lyra, and measure the brightness of more than 150,000 stars. It was not built to fly past planets. It was built to notice shadows. The instrument at the heart of Kepler was a photometer. A photometer measures light very carefully. In Kepler's case, it watched for tiny dips in starlight, so small they could be missed by almost anything less patient. When a planet passes in front of its star from our point of view, the star dims by a tiny amount. This is called a transit. The planet is not seen directly. Its presence is inferred from the missing light. For a large planet like Jupiter, the dip is easier to measure. For an Earth-sized planet crossing a Sun-like star, the dip is extremely faint. Earth passing in front of the Sun would block only about 84 parts per million of the Sun's light. That is less than 1/100th of 1%. Kepler's job was to catch changes that small, then wait to see if they happened again. A single dip could be noise, a stellar flare, an instrument artifact, or another unrelated event. A repeated dip, arriving on a steady schedule, could reveal an orbiting planet. If the dip came every 10 days, the planet likely orbited every 10 days. If it came every year, the planet needed a full year to circle its star. This repetition turned faint shadows into possible worlds. Over time, Kepler produced thousands of planet candidates. A candidate is an object that looks like a planet in the data, but still needs follow-up work before scientists can be confident. Some candidates were confirmed with other telescopes. Others were validated statistically by checking how unlikely a false signal would be. The important shift was larger than any single planet. Before Kepler, planet hunting often felt like collecting rare discoveries one at a time. After Kepler, astronomers could begin asking how common planets were as a group. They could estimate occurrence rates. An occurrence rate is a way of asking how often a certain kind of planet appears around a certain kind of star. How often do stars have giant planets? How often do they have small planets? How often do they have planets with orbits that place them near the temperature range where liquid water could exist? Kepler's patch of sky was only a small window into the Milky Way. It did not survey every star. Its method also had a built-in limitation. A transit is visible only when a planet's orbit lines up so the planet crosses the face of its star from Earth's viewpoint. Many planets orbit at angles that never create a visible transit for us. So when Kepler found thousands of candidates in one carefully watched field, the hidden meaning was larger than the catalogue itself. For every planet Kepler saw, many more would be missed because their orbits were tilted the wrong way. That changed the emotional weight of the search. The galaxy no longer looked like a place where planets might occasionally appear. It began to look like a place where planets are part of the normal architecture of stars. Kepler found hot worlds close to their stars. It found giant planets in tight orbits. It found compact systems where several planets cross the same star in repeating patterns. Most importantly for this story, it found small worlds. Planets close to Earth size. Planets that suggested rocky bodies might be common. Planets whose orbits placed them in the region where starlight could, under the right conditions, allow surface water. This did not prove those planets were alive. It did not prove they had oceans, air, continents, or anything familiar on their surfaces. But it changed the scale of the mystery. Earth was no longer being compared with one strange hot Jupiter around 51 Pegasi. It was being compared with a growing population of worlds, a statistical crowd, a galaxy of possibilities. Kepler gave scientists something more powerful than a single discovery. It gave them a way to count. And once counting made planets feel common, the search became more precise. The issue was no longer whether other worlds existed around other stars. The issue became which of those worlds sat in the narrow region where water could survive. Kepler made the galaxy feel crowded with planets. But once scientists could count worlds, they needed a way to sort them. The first major filter is called the habitable zone. Sometimes people call it the Goldilocks zone. The idea is simple. Around every star, there is a region where a planet could receive the right amount of energy for liquid water to exist on its surface. Too close, and water is more likely to boil away. Too far, and water is more likely to freeze. Somewhere between those extremes, sunlight can warm a rocky planet gently enough for oceans, lakes, or rain to become possible. That region is the habitable zone. Earth sits inside the habitable zone of the Sun. It orbits at an average distance of about 93 million miles, or about 150 million kilometers. Astronomers call that distance one astronomical unit. At that distance, Earth receives enough sunlight to keep much of its surface water liquid across billions of years. That matters because every living organism we know depends on liquid water. Bacteria need it. Plants need it. Animals need it. Inside every cell, water acts like a chemical meeting place. It lets molecules move, dissolve, react, and build the machinery of life. So when astronomers search for another Earth, they often begin by asking a basic physical question. Could liquid water survive there? That question sounds narrow, but it cuts through an enormous amount of space. A planet close to its star may receive thousands of times more energy than Earth. Some worlds orbit so tightly that their years last only a few days. Their surfaces may be hot enough to melt metals or strip lighter gases into space. A planet far from its star may receive so little warmth that water becomes locked under ice. Mars gives us a familiar example. It orbits farther from the Sun than Earth does, at about 1.5 astronomical units. Today, its surface is cold and dry, with water mostly frozen as ice or trapped in minerals. That does not make Mars useless for science. It makes Mars a reminder that distance matters. But the habitable zone is not fixed in one place. It moves depending on the star. A small red dwarf is much cooler and dimmer than the Sun. To receive enough warmth, a planet around that kind of star must orbit very close. Its habitable zone is tucked near the star, where orbits can last days or weeks. A brighter star pushes the habitable zone farther away. A planet around a star larger and hotter than the Sun might need a wider orbit to avoid receiving too much energy. So the habitable zone is really a relationship. It depends on the brightness of the star and the distance of the planet. That is why Proxima b can orbit its star every 11 days and still be discussed as a possible habitable zone planet. Its star is so faint compared with the Sun that the zone of possible warmth sits close in. The same phrase can describe very different environments. Around a Sun-like star, the habitable zone may feel familiar. Around a red dwarf, it can place a planet close enough for tidal locking, flares, and atmospheric damage to become serious concerns. Even Earth's own habitability depends on more than distance. Our atmosphere traps some heat through the greenhouse effect. Without greenhouse gases like carbon dioxide and water vapor, Earth's average surface temperature would be far below freezing. With too much greenhouse warming, oceans can evaporate and a planet can become hostile. Venus shows how severe that path can become. It orbits closer to the Sun than Earth, and its thick carbon dioxide atmosphere helps keep its surface around 860 degrees Fahrenheit. That is hot enough to melt lead. Venus sits near the inner region of the Sun's habitable zone discussions, but its surface is nothing like a second Earth. The phrase habitable zone carries hope because it points to the right kind of starlight. It also carries uncertainty because starlight is only one part of the story. A planet needs the right pressure to keep water stable. It needs an atmosphere that can survive. It needs a surface where liquid water can gather. Its history matters too, because a world may have lost its oceans long before we ever detected. So when scientists say a planet is in the habitable zone, they are describing a possibility, a first opening. a place where the conditions may allow something important to happen. The label does not tell us whether the planet has blue oceans, breathable air, continents, clouds, or life. It only tells us where to look more carefully. And that is where the search becomes more delicate. Because a planet can sit in the right ring of warmth around its star, while still being nothing like Earth. That is why the phrase Earth-sized has to be handled carefully. It sounds powerful. It sounds almost familiar. When people hear it, they naturally picture a blue world, a round ocean planet, with clouds, continents, weather, and maybe something alive moving under its sky. In astronomy, Earth-sized usually means something much narrower. It often means the planet has a radius close to Earth's radius. Radius is the distance from the center of a planet to its surface. Earth's radius is about 3,959 miles, or about 6,371 kilometers. So if a distant planet blocks about the right amount of starlight, scientists may estimate that it is roughly Earth-sized. That is a useful measurement. It gives the planet a scale. It tells us we are dealing with something closer to Earth than to Jupiter. But radius alone leaves most of the world hidden. A planet can be close to Earth's size and still have a completely different interior. It could be a dense rocky planet with an iron core like Earth. It could be rich in water with deep global oceans and layers of high-pressure ice far below the surface. It could be a bare rock, stripped of air by radiation from its star. It could also be wrapped in a thick atmosphere of hydrogen and helium, making it more like a small Neptune than a true rocky Earth. This is where mass becomes important. Mass tells scientists how much material a planet contains. Earth has a mass of about 5.97 sextillion metric tons. That number is too large to picture easily, but it matters because mass gives gravity its strength. A planet with more mass can hold onto an atmosphere more easily. A planet with less mass may lose lighter gases to space over time, especially if it is close to an active star. When scientists know both radius and mass, they can estimate density. Density is how much material is packed into a given volume. A bowling ball and a beach ball can be similar in size, but their densities are completely different. Planets work the same way. A world with Earth size and Earth-like density is more likely to be rocky. A world with a lower density may contain large amounts of gas, ice, or water. This is one reason super-Earths and mini-Neptunes are so difficult to classify. A super-Earth is usually a planet larger than Earth, but smaller than Neptune. The name can be misleading because it describes size or mass, rather than habitability. A super-Earth may be rocky. A super-Earth may have crushing gravity, thick clouds, or no friendly surface at all. A mini-Neptune is also smaller than Neptune, but it may have a deep atmosphere, a hot interior, and no clear solid ground where life like ours could live. The strange part is that these in-between worlds seem common. Our own solar system has small rocky planets like Mercury, Venus, Earth, and Mars. It also has giant planets like Jupiter, Saturn, Uranus, and Neptune. There is no planet between Earth and Neptune here at home. Yet around other stars, planets in that middle range appear again and again. That means our own neighborhood may be missing one of the galaxy's most common planet types. So when a headline says an Earth-sized planet has been found, The discovery is important, but the label is only the beginning. Scientists still need to ask what the planet weighs. They need to ask how dense it is. They need to ask whether it has an atmosphere. They need to ask whether that atmosphere is thin, thick, poisonous, stable, or already gone. They need to ask whether liquid water could actually remain on the surface, rather than existing only as ice, vapor, or deep hidden ocean. The word Earth-like becomes fragile under that pressure. It has to survive measurement after measurement. Size, mass, density, orbit, star type, atmosphere, temperature, history. A true second Earth would need more than the right width. It would need the right kind of body, in the right kind of place, around the right kind of star, with enough time for chemistry to become something more. And before scientists can know any of that, they first have to catch the planet from across light years of space. They have to find it without visiting it. They have to measure a world that appears only as a tiny change in light. So the next part of the search begins with shadows. A distant planet usually appears to us as a slight loss of light. Imagine a star sitting many light years away. Its actual surface is too far away to resolve clearly with ordinary planet hunting methods. The planet beside it is even harder to see because the star is brighter by an enormous margin. So astronomers often look for the moment when the planet passes in front of the star from our point of view. This crossing is called a transit. During a transit, the planet blocks a tiny fraction of the star's light. The star dims, then brightens again when the planet moves away from the face of the star. If you plotted that brightness on a graph, the line would stay mostly steady, then dip slightly, then rise back up. That graph is called a light curve. A light curve is one of the quietest ways a planet can announce itself. The dip may be extremely small. When an Earth-sized planet crosses a sun-like star, it blocks only about 84 parts per million of the star's light. That is like noticing a tiny insect passing in front of a bright lamp from far across a field. The telescope has to stay steady. The star has to be measured again and again. The signal has to repeat. One dip could come from instrument noise, star spots, or another object crossing the star. A second dip at the right time makes the pattern more interesting. Several dips, spaced evenly, can reveal the rhythm of an orbit. If the brightness drops every 10 days, the planet likely takes 10 days to circle the star. If the drop repeats every 365 days, the orbit may be similar in length to Earth's year. That timing gives scientists the planet's orbital period. The depth of the dip gives them the planet's size relative to the star. A larger planet blocks more light. A smaller planet blocks less. With careful measurements of the star itself, astronomers can estimate the planet's radius. This is how a world becomes Earth-sized in the data. A small shadow crosses a star. The shadow repeats. The amount of missing light is measured. From that faint pattern, scientists begin to estimate the width of a planet no spacecraft has ever visited. Kepler was built around this method. Launched in 2009, it watched more than 150,000 stars in a fixed region of sky. For years, it waited for these small, repeating dimmings. That patience turned into thousands of planet candidates. Then, in 2018, NASA launched the Transiting Exoplanet Survey satellite, usually called TESS. TESS uses the same basic idea, but surveys bright nearby stars across much more of the sky. Kepler showed how common planets could be in one deep field. TESS helps find planets around stars close and bright enough for follow-up observations. The transit method has one important requirement. The planet's orbit has to line up correctly from Earth's viewpoint. Many planets pass above or below the face of their star from where we are watching. Those worlds may exist, but they never create a visible transit for our telescopes. So every transit detection carries a hidden implication. The planets we find this way are only the ones with the right geometry. Many others are missed because their orbits are tilted differently. Even when the alignment works, the transit gives only part of the planet's story. It can reveal size. It can reveal timing. It can suggest how close the planet is to its star. The shadow leaves the surface unseen. The air remains uncertain. The oceans, if they exist, stay hidden. Life leaves no clear mark in the basic dip itself. Most alien worlds begin this way, as tiny losses of light, as repeated dimmings on a graph, as a pattern so small that the entire planet is known first by the darkness it briefly creates. That is enough to say a world is there. It is enough to estimate its width. But width is only the first measurement. To understand whether a planet is heavy, rocky, icy, or wrapped in gas, scientists need to learn how strongly it pulls on its star. A planet does more than travel around a star. Its gravity also tugs on the star itself. The effect is small, because stars are massive. The Sun contains more than 99% of all the mass in our solar system. Jupiter is the largest planet here, yet the Sun is still more than 1,000 times heavier. Even so, Jupiter pulls on the Sun enough that the Sun makes a tiny motion around a shared center of mass. That shared center is called the barycenter. It is the balance point that both objects move around. For a small rocky planet, the tug is much weaker. Earth makes the Sun move at only about 9 centimeters per second. That is slower than many people walk. From light years away, detecting motion that small is extremely difficult. A giant planet close to its star creates a much stronger signal. That is why early planet hunters found many hot Jupiters before they found smaller rocky worlds. The method used to measure this tug is called radial velocity. Radial velocity means motion toward or away from the observer. If a star is pulled slightly toward Earth, its light shifts one way. If the star is pulled slightly away, its light shifts the other way. This shift is called the Doppler effect. The same basic effect changes the pitch of an ambulance siren as it approaches and then passes by. With light, the change appears as a tiny shift in color. When a star moves toward us, its light shifts slightly toward blue. When it moves away, the light shifts slightly toward red. The change is far too small for human eyes to notice. Scientists measure it with spectrographs, instruments that split starlight into precise bands of color. Inside those bands are dark lines where atoms in the star's atmosphere absorb specific wavelengths. As the star wobbles, those lines slide back and forth by tiny amounts. That sliding pattern can reveal the pull of an unseen planet. If the pattern repeats every 4 days, the planet likely orbits every 4 days. If the signal is strong, the planet is probably massive or very close to the star. If the signal is faint, the planet may be smaller, farther away, or harder to separate from the star's own activity. Stars are not perfectly still surfaces. They rotate, they flare. They have star spots, which are cooler, darker regions similar to sunspots. Their outer layers can pulse and churn. All of this can create noise in the data. For faint stars, the measurements become harder because there is less light to work with. For active stars, the wobble of a planet can be partly hidden inside the star's own restless behavior. Still, radial velocity gives astronomers something the transit method usually cannot provide by itself. It gives them a way to estimate mass. A transit can tell us the width of a planet. Radial velocity can tell us how heavy it is. Together, those measurements allow scientists to estimate density. Density is one of the most important clues in the search for another Earth. A dense planet near Earth's size is more likely to be made of rock and metal. A lower density planet may contain large amounts of gas, ice, or water. This is where a simple headline can become complicated. Two planets can be similar in width, while being completely different kinds of worlds. One may have an iron core, a rocky mantle, and a thin atmosphere. The other may have a deep hydrogen envelope, with pressure increasing downward until any familiar surface disappears. From far away, both might begin as small shadows across a star. Their masses tell a deeper story. This is why another Earth begins as a measurement problem. First comes the dimming, then comes the wobble. Then comes the difficult work of combining size, mass, orbit, star type, and atmosphere into a picture that may still remain incomplete. Even when the numbers seem promising, the uncertainty can stay enormous. The closest possible Earth-like planet shows that better than almost any other world we have found. It orbits Proxima Centauri, the nearest known star to the Sun. Proxima Centauri is about 4.2 light-years away. That means its light takes a little more than 4 years to reach Earth. In distance, that is roughly 25 trillion miles. By the scale of the galaxy, Proxima Centauri is our next-door neighbor. By the scale of human travel, it is still unreachable with anything we have built. Proxima Centauri is part of the Alpha Centauri star system, but it is much smaller and dimmer than the two brighter sun-like stars nearby. It is a red dwarf. A red dwarf is a small, cool star that burns its fuel slowly and can last far longer than stars like the Sun. Proxima Centauri has only about 12% of the Sun's mass. It gives off a tiny fraction of the Sun's visible light. From Earth, it is too faint to see with the naked eye. In 2016, astronomers announced a planet orbiting this faint nearby star. The planet became known as Proxima b. It was detected using the radial velocity method, the same kind of star wobble measurement we just explored. The planet's gravity tugs on Proxima Centauri slightly as it orbits. That tiny pull shifts the star's light back and forth, revealing the presence of a hidden world. The discovery was immediately powerful because Proxima b seemed to carry several promising clues. It was close to Earth in mass, at least slightly heavier than our planet. It orbited inside the habitable zone, and it was located around the nearest star beyond the Sun. In the simplest version of the story, the nearest star had a possible rocky planet in the right temperature region for liquid water. That sounds like exactly the kind of discovery people had been waiting for. A nearby almost Earth. A world close enough to become the natural first target in the search for life beyond the solar system. But Proxima B's promise comes with difficult conditions. Its year lasts only about 11.2 Earth days. That means the planet circles its star more than 30 times during one Earth year. It can be in the habitable zone with such a short orbit because Proxima Centauri is so dim. The planet has to stay close to receive enough warmth. That closeness changes everything. A planet orbiting so near a small star can become tidally locked. Tidal locking means the same side of the planet may always face the star, while the opposite side remains turned towards space. The Moon is tidally locked to Earth, which is why we always see the same lunar face. On Proxima b, that kind of locking could create a permanent day side and a permanent night side. One hemisphere may sit under constant red sunlight. The other may remain in long darkness. A thick enough atmosphere could move heat around the planet, carrying warmth from the day side toward the night side. A thin or missing atmosphere would make that balance much harder. The atmosphere is the key unknown. Proxima Centauri is also an active red dwarf. It produces powerful flares, sudden bursts of radiation and charged particles from the star's surface. In 2016, the same year Proxima b was announced, astronomers were already thinking about whether repeated flares could damage or strip away the planet's atmosphere over time. A close-in planet receives those outbursts from a short distance. If Proxima b has a strong magnetic field and a durable atmosphere, it may have some protection. If its air has been eroded over billions of years, the planet could be a bare, rocky world exposed to space. From Earth, we still do not know which version is real. That is what makes Proxima b so important for this story. It has enough Earth-like pieces to create hope. It also has enough missing information to resist any simple picture. Nearby, possibly rocky, possibly temperate, possibly airless, possibly hostile. Proxima b is the closest almost Earth we know, and even this world remains hidden behind uncertainty. Its existence proves that promising planets can sit right next door in cosmic terms. Its environment shows why promising does not mean familiar. And the more astronomers study planets like Proxima b, the clearer one larger problem becomes. Many possible Earths may orbit small red suns. Small red stars are everywhere. Astronomers usually call them M-dwarfs. They are the smallest normal hydrogen-burning stars, with masses ranging from about 8% of the Sun's mass to a little more than half. Because they are small and cool, they use their fuel slowly. A star like the Sun will live for about 10 billion years. Many red dwarfs can last for hundreds of billions of years, and the smallest may shine for trillions. That gives them an enormous advantage in the search for life. A stable star that lasts that long gives planets time. Time for crust to cool. Time for oceans to settle. Time for chemistry to repeat itself across huge stretches of planetary history. Red dwarfs also appear to be the most common stars in the Milky Way. Roughly 3/4 of the stars in our galaxy may belong to this small, faint class. So if planets around red dwarfs can support life, then the galaxy may contain an enormous number of possible homes. The problem begins with brightness. A red dwarf gives off far less energy than the Sun. A planet has to orbit close to receive enough warmth for liquid water. Earth takes 365 days to circle the Sun. Mercury, the innermost planet in our solar system, takes 88 days. Around many red dwarfs, a habitable zone planet may complete an orbit in only days or weeks. That tight orbit can create tidal locking. Tidal locking happens when gravity gradually slows a planet's rotation until the same side always faces the star. The Moon is locked this way to Earth, which is why the same lunar face is always turned toward us. On a close red dwarf planet, tidal locking could produce a permanent day side and a permanent night side. The day side would receive constant starlight. The night side would face space without direct warmth from the star. Near the boundary between them, sometimes called the terminator region, temperatures might be more moderate. A thick atmosphere could soften the divide by moving heat around the planet. Winds could carry warmth away from the day side and push it toward the dark hemisphere. Ocean currents, if oceans exist, could also help spread energy. A weak atmosphere would make the contrast sharper. The day side could grow hot and dry. The night side could become cold enough for gases to freeze onto the ground. Red dwarfs create another challenge. Many are magnetically active, especially when they are young. They can release flares, sudden bursts of ultraviolet light, X-rays, and charged particles from their surfaces. A flare from the Sun can disturb satellites, radio signals, and power grids on Earth. A flare from a red dwarf can hit a nearby planet from a much shorter distance. That matters because high-energy radiation can break apart molecules in an atmosphere. Water vapor can be split into hydrogen and oxygen. Hydrogen is light, so it can escape into space more easily. Over long periods of time, this process can dry a planet out. The star's wind adds more pressure. A stellar wind is a stream of charged particles flowing outward from a star. Earth has a magnetic field that helps deflect much of the solar wind before it can directly strip our atmosphere. That magnetic shield is produced by motion inside Earth's liquid outer core. A red dwarf planet may need something similar. Without a protective magnetic field, its upper atmosphere can be eroded more easily, especially during intense stellar activity. With enough protection, a close-in world might keep its air for billions of years. With too little, it may end up as exposed rock. This is why red dwarf planets are so difficult to judge from a distance. Their stars are common. Their planets are easier to detect because the stars are small. Their habitable zones create many tempting targets. Their environments can also be harsh in ways Earth never had to endure. The same closeness that gives a planet warmth can also place it inside a storm of radiation and charged particles. So the central issue becomes simple and severe. A possible Earth around a red dwarf may be alive only if it has kept its atmosphere. Air becomes the dividing line between a world with weather, pressure, and liquid water, and a world reduced to stone. From light years away, that is the measurement scientists need most. They have to search for a planet's air inside the tiny amount of starlight that reaches us. That tiny amount of starlight carries more information than it first seems. When astronomers want to study a distant atmosphere, they use a technique called spectroscopy. Spectroscopy means breaking light into its separate wavelengths, like spreading sunlight through a prism. Each gas interacts with light in its own specific way. Some wavelengths pass through easily. Others are absorbed by atoms and molecules. The missing wavelengths create dark marks in the spectrum, called absorption lines. Those lines act like chemical fingerprints. Water vapor leaves one pattern. Carbon dioxide leaves another. Methane, oxygen, and ozone each affect light in different places. So even when the planet itself is too far away to see clearly, its atmosphere can leave a faint signature inside the star's light. The most useful moment comes during a transit. As the planet crosses in front of its star, a thin ring of starlight passes through the planet's atmosphere before reaching the telescope. That ring is incredibly small. For an Earth-sized planet around a sun-like star, the atmosphere is only a tiny shell around a tiny disk, crossing a much larger star. Yet some of the star's light filters through that shell. Molecules in the atmosphere absorb certain wavelengths. The telescope collects the altered light. Then scientists compare it with the star's normal light. The difference can reveal what gases may be present. This is called transmission spectroscopy. It is one of the main ways astronomers try to read the air of worlds they cannot visit. The method is delicate because the signal is buried inside overwhelming brightness. A star can be thousands or millions of times brighter than the planet beside it. The atmosphere itself blocks only a small fraction of the total light. A telescope has to measure the star before the transit, during the transit, and after the transit. Then scientists subtract one measurement from another with extreme care. Small errors matter. A slight change in the telescope's temperature can affect the data. Activity on the star can confuse the signal. Star spots, flares, and bright active regions can make a planet's atmosphere appear different than it really is. Even the planet's clouds or hazes can hide the deeper atmosphere from view. This is why one measurement rarely settles everything. Scientists often need several transits. For planets with short orbits, that may be possible within months or years. For planets with Earth-like year lengths around Sun-like stars, waiting for repeated transits can take much longer. The James Webb Space Telescope was built for extremely sensitive infrared astronomy. It launched on December 25, 2021, and now operates near a gravitational balance point about 1 million miles from Earth. Its main mirror is 6.5 meters wide, much larger than the Hubble Space Telescope's 2.4-meter mirror. That large mirror helps Webb collect faint light from distant objects. Its infrared instruments are especially useful for studying molecules such as water vapor, carbon dioxide, and methane. Webb has already begun measuring atmospheres around exoplanets. Some are large, hot planets that are easier to study. Others are smaller worlds where the signal is much more difficult. For Earth-sized planets, Webb is working near the edge of what current technology can do. It can test some atmospheres around small stars. It can rule out certain thick atmospheres in favorable cases. It can sometimes detect molecules around larger planets. A true Earth twin around a Sun-like star remains far harder. The planet is small. The orbit is long. The star is bright. The atmosphere is thin. Still, this is the path from planet counting to planet understanding. A shadow tells us a world exists. A wobble gives us part of its weight. A spectrum may begin to tell us whether it has air and what that air contains. The search has become a careful attempt to read chemistry from a pinprick of light. And the best nearby laboratory for this problem is a small red star surrounded by 7 Earth-sized worlds. TRAPPIST-1 sits about 40 light-years away, in the constellation Aquarius. It is an ultra-cool dwarf star, far smaller and dimmer than the Sun. Its mass is only about 9% of the Sun's mass. Its surface temperature is much lower than the Sun's, giving it a faint reddish glow instead of bright yellow-white light. In 2016, astronomers announced 3 possible planets around this star. The observations came from a small ground-based telescope called TRAPPIST, located at La Silla Observatory in Chile. The name stands for Transiting Planets and Planetesimal Small Telescope. Then the system became far more remarkable. In 2017, NASA announced that the star had 7 Earth-sized planets. The planets were named TRAPPIST-1b through TRAPPIST-1h, in order from closest to farthest from the star. This was the largest group of Earth-sized planets ever found around a single star. For the search for other Earths, it felt like a perfect natural laboratory. 7 small worlds, 1 nearby star, several planets close enough to the habitable zone to make scientists pay careful attention. The system is extremely compact. All 7 planets orbit much closer to TRAPPIST-1 than Mercury orbits the Sun. Mercury takes 88 days to go around the Sun. The innermost TRAPPIST-1 planet, TRAPPIST-1b, orbits in about 1.5 Earth days. TRAPPIST-1c takes about 2.4 days. TRAPPIST-1d takes just over 4 days. Even the outer planet, TRAPPIST-1h, completes an orbit in less than 19 days. In our solar system, that would place all 7 planets deep inside Mercury's path. Around TRAPPIST-1, those close orbits can still make sense because the star is so dim. The warmth zone sits tucked close to the star. Planets E, F, and G are often discussed as the most interesting habitable zone candidates, though each still depends on atmosphere, pressure, and history. The planets also appear to move in a linked rhythm. Their orbits are arranged in a chain of resonances. Orbital resonance means planets tug on each other in repeating patterns because their orbital periods line up in simple ratios. In the TRAPPIST-1 system, those repeated gravitational tugs help scientists estimate the planet's masses. The timing of each transit shifts slightly because neighboring planets pull on each other. Those tiny timing changes carry information about weight. That made TRAPPIST-1 especially valuable. Astronomers could measure sizes from transits, then estimate masses from the way the planets disturbed each other's schedules. With size and mass together, they could begin estimating density. Density helps separate rocky worlds from worlds with large amounts of gas or water. Small stars make this kind of study easier in one important way. When an Earth-sized planet crosses a small star, it blocks a larger fraction of the star's light. The shadow is deeper. The signal is easier to measure. Around a Sun-sized star, An Earth-sized planet creates a tiny dip. Around an ultra-cool dwarf, that same planet covers a more noticeable part of the star's face. That is why TRAPPIST-1 became so important for Webb and other telescopes. The system gives scientists several Earth-sized planets around a star small enough for detailed transit observations. From a distance, it almost looks like the dream version of the whole search. A nearby red star, a family of rocky-sized planets, orbits that repeat often enough to study again and again, possible habitable zone worlds waiting for atmospheric tests. Yet every promising detail carries pressure. These planets orbit close to an active small star. Several may be tidally locked. Their atmospheres may have been damaged by radiation over billions of years. Some may have kept air. Some may have lost it. Some may have surfaces shaped by conditions we have never seen up close. TRAPPIST-1 compresses the entire mystery into one system. It shows why possible Earths may be common enough to find in groups. It also shows why every possible Earth has to survive a harder test. From far away, the system looks like a treasure chest of small worlds. Closer measurements begin asking what each planet actually managed to keep. With Webb, that test became more direct. One of the first TRAPPIST-1 worlds to face it was TRAPPIST-1c. This planet is the second world out from the star. It orbits in about 2.4 Earth days. It is close enough to TRAPPIST-1 that it receives a strong amount of heat, more similar to Venus than to Earth. That makes it useful for a particular kind of measurement. Astronomers can watch the system as the planet moves behind the star. This event is called a secondary eclipse. During a normal transit, the planet crosses in front of the star and blocks a little starlight. During a secondary eclipse, the planet disappears behind the star for a short time. Just before it disappears, the telescope receives light from the star, plus heat coming from the planet's day side. When the planet slips behind the star, only the star remains. By comparing those two measurements, scientists can estimate how much heat the planet itself was giving off. That heat is called thermal emission. It is infrared light, the kind of light associated with warmth. Webb is especially powerful in infrared wavelengths, which made it the right tool for this work. For TRAPPIST-1c, Webb measured the planet's dayside heat and compared it with what different atmosphere models predicted. A thick carbon dioxide atmosphere would affect that heat. Carbon dioxide traps infrared energy. On Venus, a dense carbon dioxide atmosphere helps keep the surface extremely hot, around 860 degrees Fahrenheit. A thick atmosphere can also move heat around a planet. Winds can carry energy from the day side toward the night side. That redistribution changes the temperature pattern Webb would detect. The measurement from TRAPPIST-1c did not match a thick Venus-like carbon dioxide atmosphere. The result stripped away one of the more hopeful possibilities for that planet. TRAPPIST-1c may have a much thinner atmosphere. It may have a different kind of atmosphere that is harder to detect. It may be close to bare rock. Each possibility means something different, but the main lesson is already clear. An Earth-sized planet can lose the very thing that would make its surface matter. A rocky body without a substantial atmosphere has no familiar weather. Surface water becomes difficult to keep stable. Heat escapes quickly into space on the night side. Radiation reaches the ground more easily. From far away, the planet can still look promising in the catalogue. Its size can still be close to Earth's. Its orbit can still be measured precisely. Its star can still make it valuable for study. Then, a better observation can remove part of the dream. That is what makes TRAPPIST-1 so important. It does not simply give scientists a group of possible Earth-sized worlds. It gives them a way to watch those possibilities become more specific. A planet stops being a hopeful label and becomes a physical place with constraints. TRAPPIST-1c shows how a small rocky world close to a red dwarf may have struggled to keep its air. Over billions of years, stellar radiation can heat the upper atmosphere. Charged particles from the star can push against it. Lighter gases can escape into space. If the planet began with water, some of that water could have been broken apart by high-energy light. Hydrogen would escape most easily, leaving the planet drier over time. This is the difficult part of the search. Better instruments do not always make a world more Earth-like. Sometimes they make the loss easier to see. Sometimes they turn a candidate into a warning. TRAPPIST-1c does not settle the entire system. Other planets there may have different histories. TRAPPIST-1, E, F, and G orbit farther out, where conditions may be less extreme. Their atmospheres still need to be tested. Their surfaces remain unknown. Yet Webb has already shown how careful the word Earth-sized must be. A planet can have the right scale and still be missing the layer that separates a living surface from exposed stone. Once air becomes uncertain, water becomes uncertain with it. And even a world that holds water somewhere may still be very different from a place where life can easily begin. Water is the clue that feels most like a promise. Every living thing on Earth depends on it. Inside cells, water lets molecules dissolve, move, collide, and react. It carries nutrients through blood. It fills the cytoplasm inside bacteria. It helps proteins fold into useful shapes. So when astronomers talk about habitability, water naturally becomes the first substance they look for. But water is not one condition. It is many possible conditions wearing the same name. On one planet, water may be vapor high in the atmosphere. On another, it may be locked as ice across the surface. On another, it may sit as a deep ocean under a frozen crust. On a very massive ocean world, water may be crushed into exotic forms of high-pressure ice far below the surface. That kind of ice does not form because the water is cold. It forms because the pressure is enormous. Deep inside a planet with hundreds or thousands of miles of water, the weight above can force water molecules into solid crystal structures even at temperatures where ordinary ice would melt. That matters because life needs more than the presence of water. It needs water in a place where chemistry can stay active. It needs contact with useful elements. It needs an energy source. It needs conditions stable enough for reactions to repeat over long periods of time. Our own solar system shows how complicated this becomes. Europa, one of Jupiter's large moons, is slightly smaller than Earth's moon. Its surface is covered in ice, crossed by long cracks and reddish-brown streaks. Beneath that ice, scientists think Europa has a global saltwater ocean. The ocean may contain more water than all of Earth's oceans combined. Jupiter's gravity flexes Europa as it orbits, squeezing and stretching the Moon's interior. That flexing creates heat. The process is called tidal heating. It may keep Europa's hidden ocean liquid under a crust that could be several miles thick. Enceladus, a small moon of Saturn, gives an even more dramatic example. It is only about 310 miles wide, yet NASA's Cassini spacecraft saw geysers erupting from cracks near its south pole. Those plumes sprayed water vapor, ice grains, salts, and organic molecules into space. Cassini flew through some of that material and found evidence pointing to a subsurface ocean beneath the ice. So Europa and Enceladus are water-rich worlds. They are also deeply different from Earth. Their oceans are buried. Their skies are absent or extremely thin. Their surfaces are frozen. Any life there, if it exists, would likely be hidden in dark water under ice, possibly near seafloor chemistry, rather than sunlight. That is a very different picture from a planet with rain, clouds, shorelines, and exposed continents. Surface liquid water matters because it allows the atmosphere, surface rocks, sunlight, and chemistry to interact directly. On Earth, rain falls through air, reacts with carbon dioxide, weathers rocks, carries minerals into rivers, and eventually feeds oceans. That slow exchange helps regulate climate over geological time. It gives life access to energy and nutrients across many environments. Pressure is essential too. Liquid water can remain stable only under the right temperature and pressure. Mars shows the problem clearly. Its surface pressure today is less than 1% of Earth's. Under such thin air, liquid water struggles to remain on the surface for long. It tends to freeze, evaporate, or boil away. Venus shows the opposite danger. A thick carbon dioxide atmosphere created a severe greenhouse effect, trapping heat until the surface became hot enough to melt lead. Water may once have existed there, but the planet became a warning about how atmosphere can transform a world. So when scientists detect water vapor, ice, or a possible ocean, they have found an important clue. They have not found a living planet. The clue has to be placed inside a larger system. Temperature decides whether water freezes, flows, or evaporates. Pressure decides whether liquid can stay stable. Atmosphere decides whether the surface is protected or exposed. Chemistry decides whether useful reactions are available. Energy decides whether those reactions can keep going. Water remains one of the best signs to search for because every life form we know depends on it. But water alone cannot carry the whole burden of proof. The search has to move from possible habitability into something harder to fake. It has to look for the chemical traces that living worlds might leave behind. These traces are called biosignatures. A biosignature is a sign that could point toward life. It may be a gas in the atmosphere. It may be a chemical pattern on a surface. It may be a combination of molecules that seems difficult to maintain without biology constantly renewing it. For distant exoplanets, atmospheres are the most practical place to look first. Air can carry evidence across an entire world. If life changes a planet's chemistry strongly enough, that change may become visible from light years away. Earth gives the clearest example. About 21% of Earth's atmosphere is oxygen. Most of that oxygen exists because of photosynthesis. Photosynthesis is the process used by plants, algae, and some bacteria to capture sunlight and turn carbon dioxide and water into sugars. Oxygen is released as a byproduct. For more than 2 billion years, tiny ocean microbes called cyanobacteria helped change Earth's atmosphere. They released oxygen into the seas and air until the planet became chemically different from the world it had been before. That oxygen also created ozone. Ozone is a molecule made of 3 oxygen atoms. High in Earth's atmosphere, the ozone layer absorbs much of the sun's harmful ultraviolet radiation. So oxygen and ozone can both become signs that something powerful has changed a planet's air. Methane adds another layer. On Earth, methane comes from several sources. Some is produced by microbes living in oxygen-poor places, such as wetlands, sediments, and the digestive systems of animals like cows and termites. Some comes from geology, including reactions between water and certain rocks deep underground. Methane matters because it does not last forever in an oxygen-rich atmosphere. Given enough time, oxygen and sunlight help break methane down. So if a planet has both oxygen and methane in meaningful amounts, scientists pay close attention. Those gases tend to react away from each other. Keeping both present may require active replenishment. This is called chemical disequilibrium. Disequilibrium means the atmosphere is out of easy chemical balance. A dead planet can have gases. A living planet may keep pushing its gases away from balance. That is the deeper reason biosignatures are so interesting. Life does not simply sit on a planet. It can alter the entire atmosphere. It can take in gases, release gases, and reshape chemistry over millions or billions of years. A telescope cannot see a forest on a world dozens of light years away. It may be able to see the atmospheric consequence of life doing chemistry at planetary scale. Carbon dioxide is part of this picture too. It is a greenhouse gas, meaning it traps heat and helps warm a planet's surface. Earth has carbon dioxide in small amounts. Mars has a thin atmosphere made mostly of carbon dioxide. Venus has an extremely thick carbon dioxide atmosphere. The same molecule can mean very different things depending on pressure, temperature, and planetary history. That is why biosignatures require caution. Oxygen can be created by living organisms, but some non-living processes can also produce oxygen under certain conditions. Ultraviolet light from a star can split water vapor into hydrogen and oxygen. Hydrogen can escape into space more easily, leaving oxygen behind. A planet that lost its water long ago might build up oxygen without having life. Methane can come from microbes, but it can also come from volcanic activity or chemical reactions involving rock and water. Ozone can suggest oxygen, but oxygen still needs context. Carbon dioxide can help warm a planet or mark a world with a crushing greenhouse atmosphere. Every gas has to be interpreted with the planet around it. The star matters. The orbit matters. The temperature matters. The planet's mass and atmosphere matter. A true biosignature is strongest when several clues fit together. Scientists would want to see gases that make sense in a living system and resist simpler geological explanations. That is what makes the search so delicate. A possible biosignature would be one of the most important discoveries in human history. It would also be one of the most carefully challenged. Every natural explanation would have to be tested. Every instrument effect would have to be checked. Every stellar complication would have to be understood. The first hint of life beyond Earth may arrive as a small chemical mismatch in a faint spectrum. A missing color, a suspicious gas, a pattern in the air of a world no one has ever seen directly. And when a planet finally shows interesting gases, the answer can still remain painfully complicated. K218b is one of those complicated worlds. It orbits a cool red dwarf star about 120 light-years from Earth, in the constellation Leo. The planet was first identified by the Kepler Space Telescope's extended mission, known as K2. Its name comes from that mission. K2-18 is the star. The letter B marks the first confirmed planet found around it. At first glance, the planet has several features that make it interesting. It orbits inside the star's habitable zone. It takes about 33 days to complete one trip around its star. It is much larger than Earth, with about 8.6 times Earth's mass and a radius more than twice Earth's. That puts it in an awkward category. Too large to feel like a simple Earth copy. Small enough to remain very different from Neptune. In 2019, observations from the Hubble Space Telescope found evidence of water vapor in its atmosphere. That made K218b one of the first habitable zone exoplanets where atmospheric water became part of the discussion. Then, Webb added a deeper layer. Using infrared spectroscopy, Webb detected methane and carbon dioxide in the planet's atmosphere. Those gases mattered because they helped scientists think about what kind of world K218b might be. The planet may have a hydrogen-rich atmosphere. Hydrogen is the lightest element, and a thick hydrogen envelope can make a planet very different from Earth. Under that atmosphere, some models suggest K218b could have a global ocean. A world like that is sometimes called Haitian. The word combines hydrogen and ocean. A Haitian planet would have a hydrogen-rich sky above a possible water-covered surface. That is an unusual idea because it expands the imagination of habitability. Life on Earth lives under a nitrogen-oxygen atmosphere. A Haitian world would have a very different kind of air. It might have higher pressure. It might have a warmer upper atmosphere. Its ocean, if present, could sit beneath a deep blanket of gas. From far away, methane and carbon dioxide do not settle the entire picture. They are clues. They suggest chemistry. They help narrow the range of possible atmospheres. They also leave room for disagreement. Some scientists interpret K218b as a possible ocean world. Others argue that it may be closer to a sub-Neptune. A sub-Neptune is a planet smaller than Neptune, but often large enough to hold a thick atmosphere. Many sub-Neptunes may have deep gas layers and high-pressure interiors, with no familiar surface where water could gather in an Earth-like way. This is where K218b becomes so useful for the larger mystery. It shows that atmospheric chemistry can become exciting, while the planet itself remains hard to classify. Methane and carbon dioxide are real molecules with real meaning. They can shape temperature. They can point to atmospheric structure. They can help scientists test models. But the same gases can fit more than one planetary story. A hydrogen-rich ocean world would be fascinating. A hot, gas-wrapped sub-Neptune would be fascinating in a different way. Both possibilities teach us something about the universe. Only one would move closer to the kind of habitability people usually imagine. Even the word ocean needs care here. On Earth, oceans touch rock, receive sunlight near the surface, exchange gases with the atmosphere, and interact with continents, volcanoes, and weather. On a larger planet with a thick hydrogen atmosphere, pressure could change the structure of the ocean. At great depth, water may behave differently. High-pressure ice layers could separate liquid water from the rocky interior, limiting the chemical exchange that helps make Earth's oceans so active. That detail matters because life needs more than a place to float. It needs energy. It needs useful chemistry. It needs stable conditions that allow complex reactions to continue. K2-18b is valuable because it sits between categories. It has a habitable zone orbit. It has detectable atmospheric gases. It has enough mass to hold a substantial atmosphere. It also has enough size and uncertainty to resist the simple image of another Earth. The discovery does not make the search weaker. It makes the search wider. It suggests that the universe may contain habitable candidates that do not match the blue planet in our mind. Some may be ocean worlds. Some may be gas-wrapped worlds. Some may be rocky planets with thin air. Some may belong to categories our solar system never gave us. K2-18b turns the search for another Earth into something stranger. The universe may not be full of simple Earth copies. It may be full of worlds Earth never taught us how to picture. Those unfamiliar worlds show up again and again in exoplanet catalogues. Astronomers often call them super-Earths and sub-Neptunes. A super-Earth is usually larger or more massive than Earth, while still much smaller than an ice giant like Neptune. The name sounds encouraging, but it only describes scale. It does not guarantee oceans, continents, life, or a surface where anything familiar could stand. A sub-Neptune is usually smaller than Neptune, but large enough to hold a deep atmosphere. Neptune is almost 4 times wider than Earth and about 17 times more massive. A sub-Neptune may sit somewhere below that size, wrapped in hydrogen and helium, with pressure increasing downward into layers we have never visited. This is one of the strange lessons of planet hunting. Our solar system has no world in that middle range. Earth is the largest rocky planet here. Neptune is the smallest giant planet. Between them, there is a missing category. No planet 2 times Earth's radius. No planet 3 times Earth's radius. No nearby example of the type that appears to be common around other stars. That gap in our own system can mislead us. For centuries, the solar system was the only planetary architecture we knew. Small rocky worlds close to the sun. Giant planets farther out. Icy bodies beyond them. Then, exoplanet surveys began finding systems that did not follow that familiar pattern. Close-in gas giants. Compact chains of small planets. Rocky worlds larger than Earth. gas-wrapped planet smaller than Neptune. A planet between Earth and Neptune can take several forms. It may be a dense rocky super-Earth with a large iron core and stronger surface gravity. It may be a water-rich world, with oceans hundreds of miles deep. At the bottom of those oceans, pressure could create layers of high-pressure ice, separating liquid water from rock. That separation would matter because Earth's oceans are chemically alive, partly because water touches minerals, vents, sediments, and crust. Another planet in that size range may have started rocky, then kept a hydrogen envelope from the gas disk that surrounded its young star. A hydrogen envelope can make the planet look larger during a transit. It can also create crushing pressure far below the upper atmosphere. A world like that may have no clear Earth-like surface, even if its size first sounds promising. The radius gap helps astronomers sort this problem. When scientists plotted many Kepler planets by size, they noticed fewer planets around roughly 1.5 to 2 Earth radii. Many planets cluster below that range. Many others sit above it. This dip is often called the radius gap or the Fulton gap. It may be a clue that planets split into different evolutionary paths. Smaller planets can lose their light gases and become exposed rocky cores. Larger planets can hold on to thicker hydrogen-rich atmospheres and become sub-Neptunes. Starlight plays a major role. Young stars give off intense ultraviolet and X-ray radiation. That energy can heat the upper atmosphere of a close planet until gas escapes into space. This process is called photoevaporation. Another possibility is core-powered mass loss, where heat left over from a planet's formation helps drive atmosphere away over time. Both processes can strip some planets down while leaving others wrapped in gas. That means two planets born in similar systems can age into very different worlds. One becomes rocky and compact. Another keeps a thick atmosphere. A third may hold so much water that its interior becomes layered in unfamiliar ways. This makes Earth feel less like the standard pattern and more like one outcome among many. Earth has the right size to keep an atmosphere without becoming gas-wrapped. It has enough gravity to hold air, yet a surface still exposed to sky, ocean, and rock. That balance may be common. It may be rare. Current catalogues contain too many partial measurements to settle the issue cleanly. So the search for another Earth has to pass through these strange middle worlds. They fill the space between categories. They remind us that planet formation produces more variety than our local neighborhood reveals. And if so many worlds fall between familiar types, estimating the number of true Earth-like planets becomes much harder. That estimate begins with a strange act of translation. Kepler watched one small region of the sky. Its main field sat near the constellations Cygnus and Lyra, along one crowded part of the Milky Way. Inside that field, the telescope measured the brightness of more than 150,000 stars. That sounds like an enormous survey. Compared with the whole galaxy, it was a narrow sample. The Milky Way contains somewhere between 100 billion and 400 billion stars. Kepler studied a tiny fraction of them with unusual patience. Its discoveries had to be corrected for what the telescope could miss. The transit method depends on alignment. A planet has to pass across the face of its star from our point of view. Many planets orbit at angles that never produce a transit for Earth. Those planets could be common, yet invisible to Kepler's method. There is also a timing problem. A planet close to its star crosses often. A planet with a 10-day orbit gives many chances to detect repeated dips. A planet like Earth, orbiting once every year, produces only one transit every 365 days. Kepler needed at least several repeated events to build confidence. That made long-orbit planets harder to confirm, especially when the mission had a limited observing lifetime. Small planets created another difficulty. An Earth-sized world crossing a Sun-like star blocks only about 84 parts per million of the star's light. Instrument noise, stellar activity, and small brightness changes on the star itself can hide signals that faint. So Kepler's catalogue was never a complete list of planets in its field. It was a measured sample shaped by geometry, time, brightness, and instrument sensitivity. Astronomers then used statistics to ask what the missing population must look like. If Kepler saw a certain number of transiting planets, and only a small fraction of planetary systems line up for transits, then many more planets should exist with orbits tilted away from us. This is how a small patch of sky became a way to estimate the galaxy. The result was startling. Planets appeared to be normal companions of stars. Small planets appeared to be common. Some studies using Kepler data suggested that roughly 1 in 5 Sun-like stars could have an Earth-sized planet receiving a similar amount of starlight to Earth. That estimate carries uncertainty. Different studies define Earth size differently. Some use slightly wider size ranges. Some define the habitable zone more generously or more conservatively. The number changes depending on how scientists correct for missed planets and false signals. Even with those caveats, the implication remains enormous. If even a modest fraction of Sun-like stars host Earth-sized planets in temperate orbits, the Milky Way may contain billions of possible Earth-like worlds. Around red dwarfs, the numbers could grow even larger, because those stars are so common. The count becomes difficult to picture. A single confirmed Earth-sized habitable zone planet would be historic. A galaxy containing millions or billions of candidates changes the emotional weight of the search. Each candidate is incomplete. Some may be airless, some may be frozen, some may be wrapped in thick gas, some may have oceans hidden under ice or pressure. Yet the population itself becomes impossible to ignore. The universe has produced planets in huge numbers. It has produced rocky worlds. It has placed some of them where surface water might be possible. That should make life feel easier to imagine. It should make Earth feel less isolated. Instead, the count brings us closer to a deeper silence. We have thousands of confirmed exoplanets. We have statistical evidence for far more. We have a growing list of worlds with pieces of Earth's pattern. Still, Earth remains the only known living planet. Once the possible Earths become numerous enough, the empty sky begins to feel like evidence waiting to be understood. That feeling has a name. Scientists often connect it to the Fermi paradox. The paradox is named after physicist Enrico Fermi, who was one of the major figures in 20th century physics. In 1950, while working at Los Alamos National Laboratory, Fermi was talking with other scientists about interstellar travel and alien civilizations. the discussion circled around the size of the galaxy, the age of the stars, and the possibility that intelligent life might have appeared somewhere else long before humans. Then Fermi asked the simple question that still hangs over astronomy: where is everybody? That question became powerful because the numbers seemed to point in two directions at once. The Milky Way is about 13.6 billion years old. Our solar system is about 4.6 billion years old. That leaves billions of years before Earth even formed. Other stars had time to form planets. Other planets had time to cool. Other biospheres, if they existed, had time to begin, change, and possibly develop intelligence. Even slow interstellar expansion could spread widely over galactic time. A civilization traveling far below the speed of light could still cross large parts of the Milky Way over millions of years. Millions of years sound enormous beside a human life. Beside the age of the galaxy, they are short. That is where the tension begins. Planet surveys suggest that stars commonly have planets. Kepler showed that small worlds are frequent. Red dwarfs, the most common stars in the galaxy, may host huge numbers of close-in rocky planets. Some sun-like stars may have Earth-sized worlds in temperate orbits. Across one galaxy, that could mean millions or billions of possible stages where life might begin. Each one would have its own chemistry, its own star, its own weather, if it kept an atmosphere, its own long planetary history. Given that many possible beginnings, the universe feels as though it should have produced more evidence by now. A living atmosphere somewhere, a clear biological gas pattern, a radio signal, an engineered object crossing a star, a sign that another world did what Earth did, in its own way, under its own sky. So far, no confirmed evidence has arrived. The search for extraterrestrial intelligence, often called SETI, has listened for artificial radio signals for decades. Radio telescopes have scanned stars, star clusters, and wide regions of the sky. Researchers look for signals with features nature rarely produces, such as extremely narrow frequencies, repeated patterns, or structures that appear intentionally modulated. The search has produced interesting moments, including the famous WOW signal detected in 1977. That signal lasted 72 seconds and was never confirmed again. Without repetition, it remains an unresolved event, rather than proof. No confirmed extraterrestrial transmission has been found. No verified alien beacon has been detected. No civilization has clearly announced itself from another star. That silence changes the meaning of all those possible Earths. A small number of candidates could feel like simple uncertainty. A galaxy filled with potential habitats creates a heavier problem. Maybe life is difficult to start, even on planets with water and rock. Maybe simple life begins often, while complex cells almost never appear. Maybe intelligence is rare because evolution has no requirement to produce telescopes, language, or technology. Maybe civilizations broadcast for only a short time before becoming quiet, changing their communication methods or disappearing. There is also the possibility that our instruments are still too limited. Human radio astronomy is barely more than a century old. Serious SETI searches have existed for only a tiny sliver of cosmic time. The galaxy may contain signals we have missed, signals too faint to detect, or life that leaves no obvious signature from across light years. Even so, the basic pressure remains. More possible Earths mean more places where something could have happened. More places make the absence harder to ignore. The search for another Earth is no longer only about finding a planet with the right size and orbit. It has become a way of testing whether Earth's deeper story is common, rare, or almost impossible to repeat. The first explanation is quiet, but severe. Many planets may look promising from far away, while the full Earth recipe may require a much narrower chain of conditions. This narrower chain is often called the rare Earth hypothesis. It was popularized in 2000 by paleontologist Peter Ward and astronomer Donald Brownlee. The idea is that simple life may appear on many worlds, while complex Earth-like life may need a long sequence of favorable conditions. A galaxy can make rocky planets in huge numbers. It can place many of them in temperate orbits. It can give some of them water, atmospheres, and long histories. Complex life may still require a much more specific kind of world. Earth has several stabilizing features working together. One is the Moon. Earth's moon is unusually large compared with its planet. It is about 1/4 of Earth's diameter. Its gravity helps stabilize Earth's axial tilt, which is the angle of the planet's rotation relative to its orbit. Earth's tilt is about 23.5 degrees. That tilt gives us seasons. If the tilt changed wildly over time, climates could swing more severely, making long-term stability harder for ecosystems. Earth also has plate tectonics. The crust is broken into large moving plates that slide, collide, sink, and separate over millions of years. At subduction zones, old crust sinks back into the mantle. At mid-ocean ridges, new crust forms as molten rock rises and cools. This slow movement helps recycle carbon. Carbon dioxide dissolves into rainwater, reacts with rocks, travels through rivers and oceans, and eventually becomes locked into sediments. Volcanoes return some carbon dioxide to the atmosphere. This carbon cycle helps regulate Earth's temperature over geological time. If the planet warms, chemical weathering can speed up and remove more carbon dioxide. If the planet cools, volcanic carbon dioxide can build up and warm the climate again. That feedback has helped Earth keep liquid water across billions of years, even though the young sun was dimmer than it is today. Earth also has a magnetic field. It is generated by motion in the liquid iron outer core, deep beneath the surface. That magnetic field reaches far into space and helps deflect charged particles from the solar wind. The atmosphere still loses some material over time, but the magnetic field gives Earth an important layer of protection. Mars gives a useful contrast. It lost its global magnetic field early in its history. Its atmosphere became thin, and its surface became cold and dry. Earth also orbits a stable, long-lived star. The Sun changes over time, but it has been steady enough for life to develop across roughly 4 billion years. A planet around a violently active star may have a harder time keeping air and water. A planet around a short-lived massive star may run out of time before complex life can evolve. Oceans matter too. Earth's oceans cover about 71% of the surface. They store heat, move energy around the globe, dissolve chemicals, and provide stable environments where life can persist through changing conditions. For much of Earth's history, life was microscopic. Single-celled organisms dominated for billions of years. Complex animals appeared much later, especially after oxygen became abundant enough to support larger bodies and more active metabolisms. That difference matters. A world covered in microbes would be alive. It might still leave only subtle traces across interstellar distance. Forests, animals, intelligence, and technology require additional steps. Jupiter is sometimes included in rare Earth discussions because its gravity can redirect comets and asteroids. Its role is debated. In some cases, Jupiter may protect the inner solar system by clearing dangerous objects. In other cases, its gravity may send objects inward. The important point is that giant planets can shape impact histories, and impact history can shape habitability. Large impacts can deliver water and organic material. They can also sterilize surfaces, alter atmospheres, or reset evolution. The rare Earth idea makes the exoplanet count feel different. Thousands of planets may share one or two pieces of Earth's pattern. Some may have the right size. Some may have the right orbit. Some may have water. Some may keep atmospheres for billions of years. A true Earth-like world may need many of those pieces arranged together and kept stable across immense time. So the galaxy could be full of near-Earths, worlds that came close, worlds that had oceans for a while, worlds that began with promise, then lost air, froze over, dried out, or never developed beyond simple chemistry. Many Earth-sized planets could be empty stages. And even if life does begin often, the silence may mean that most living worlds never make it very far. That possibility leads to the Great Filter. The Great Filter is the idea that somewhere between lifeless chemistry and a detectable civilization, there may be a step so difficult that most worlds never pass through it. The filter could sit very early. It could sit late. It could be a single barrier or several barriers spread across billions of years. A possible Earth may have oceans, carbon, energy, and a stable orbit, then still stop at the first step. That first step is abiogenesis. Abiogenesis means life beginning from non-living chemistry. On Earth, life appears to have started early in the planet's history, perhaps more than 3.5 billion years ago. The oldest widely discussed evidence includes ancient carbon signatures, microbial mats, and layered rock structures called stromatolites. Stromatolites can form when communities of microbes trap sediment in shallow water. They still exist today in places like Shark Bay in Western Australia. Their ancient relatives suggest that simple life was present on Earth very far back in time. That sounds encouraging. Life began here while Earth was still young. Yet one example gives us no clean probability. A process can happen quickly on one planet and still be rare across the galaxy. If abiogenesis is the filter, then many possible Earths may remain chemical worlds forever. They may have water, minerals, lightning, sunlight, and organic molecules, while never crossing into living cells. A later filter could be oxygen. For roughly half of Earth's history, the atmosphere contained very little free oxygen. Then, cyanobacteria, tiny photosynthetic microbes, began releasing oxygen as a waste product. around 2.4 billion years ago, oxygen levels rose dramatically during the Great Oxidation Event. That changed the planet. Oxygen allowed more energetic metabolisms. It also poisoned many organisms adapted to oxygen-poor environments. A living world can spend billions of years in microbial quiet before its air changes enough to support larger, more active life. Complex cells may be another barrier. Animals, plants, fungi, and algae are made of eukaryotic cells. These cells have internal structures, including a nucleus that stores DNA and mitochondria that help release energy from food. Mitochondria likely began as bacteria that entered into partnership with other cells long ago. That partnership was one of the most important events in the history of life on Earth. If that step is rare, then many living planets may remain microbial for their entire history. Multicellular life adds another narrowing. For billions of years, Earth was alive, but mostly microscopic. Large animals became common only in the last 600 million years or so. The Cambrian explosion, about 540 million years ago, brought a rapid expansion of animal body plans in the fossil record. Eyes, shells, limbs, and predators became part of the story. Before that, Earth had already been alive for an immense span of time. Intelligence may be narrower still. Dinosaurs dominated land ecosystems for more than 160 million years. They never built radio telescopes. Mammals existed through much of that age as small animals living under the shadow of larger reptiles. Only after the asteroid impact 66 million years ago did mammals diversify into many of the forms we know today. The human lineage split from chimpanzee relatives roughly 6 to 7 million years ago. Modern humans appeared only about 300,000 years ago. Radio technology is barely over a century old. That timeline matters because a technological species may be a brief phase, even on a planet with complex life. Technology creates signals. It also creates risks. Nuclear weapons appeared in 1945. Industrial activity has changed Earth's atmosphere in a measurable way. Advanced biology, artificial intelligence, and other powerful tools give civilization more ability to shape its future, while also increasing the consequences of mistakes. If the great filter lies ahead, then detectable civilizations may often become vulnerable soon after they become visible. This is why possible Earths create such a double-edged feeling. Finding many rocky worlds would be hopeful. Finding many lifeless rocky worlds would make Earth feel more unusual. Finding many living worlds with no complex life would point toward a later barrier. Finding many worlds with oxygen, water, and microbes, but no technology, would make intelligence look fragile. Each discovery would answer one part of the mystery while sharpening another. The answer may depend on whether the next generation of telescopes can find living chemistry on another world. That is why NASA is planning a mission built around this exact uncertainty. It is called the Habitable Worlds Observatory. The mission is still in development, but its purpose is already unusually clear. It is being designed to search for planets like Earth around nearby stars, then study their light for signs of habitability and possible life. Its central goal is to directly image about 25 potentially habitable worlds. Direct imaging means trying to see the planet's own light. That sounds simple until the star enters the picture. A planet like Earth is extremely faint, beside a star like the Sun. In visible light, an Earth-like planet can be roughly 10 billion times dimmer than its star. It also sits very close to the star in the sky from our point of view. At a distance of 10 light-years, the separation between an Earth-like planet and a Sun-like star would look smaller than the width of a human hair seen from many meters away. So the telescope has to perform a kind of controlled blindness. It must block the star's glare while preserving the tiny reflected light from the planet nearby. One way to do this is with a coronagraph. A coronagraph is an instrument inside a telescope that masks the bright central star, creating an artificial eclipse. The idea began with studies of the Sun's outer atmosphere, where astronomers needed to block the Sun's bright disk to see the faint corona around it. For exoplanets, the same basic principle becomes far more difficult. The telescope has to suppress starlight with extraordinary precision. Any scattered light, slight vibration, mirror imperfection, or thermal distortion can bury the planet's signal. Another possible approach is a starshade. A starshade would be a separate spacecraft flying far in front of the telescope. Its shape would block starlight before it entered the telescope, allowing the planet's faint, reflected light to stand out. A starshade would need to align across tens of thousands of miles of space with extreme accuracy. Both ideas show how hard this search has become. Finding another Earth means separating a firefly from a lighthouse across interstellar distance. Once the planet's light is isolated, spectroscopy becomes the deeper tool. The telescope can split that faint reflected light into wavelengths. Those wavelengths can reveal chemical fingerprints in the planet's atmosphere. Oxygen would matter because, on Earth, it is strongly linked to photosynthesis. Methane would matter because it can be produced by microbes, though geology can produce it too. Ozone would matter because it forms from oxygen and absorbs ultraviolet radiation. Carbon dioxide and water vapor would help scientists understand climate, greenhouse warming, and possible surface conditions. No single gas would settle the issue by itself. The power would come from combinations, oxygen together with methane, water vapor with a stable temperature range, carbon dioxide levels that make sense for a rocky planet, rather than a runaway greenhouse world. A living world may reveal itself through chemistry that keeps being replenished. A dead world may still show interesting gases, but the pattern may settle into a simpler balance. The Habitable Worlds Observatory would also search nearby stars, chosen carefully. Distance matters because closer planets are easier to separate from their stars. Star type matters because stable stars give cleaner signals. Planet orbit matters because a world has to sit where surface water could plausibly survive. This future observatory is important because it moves the search from counting possible Earths to testing them. Kepler gave statistics. TESS finds nearby candidates. Webb studies atmospheres in favorable systems. The Habitable Worlds Observatory would be built with the direct purpose of asking whether small rocky worlds around nearby stars show signs of life. That creates a strange kind of pressure. The first clear biosignature would change Earth's place in the universe forever. A long search through nearby candidates with no living chemistry would also mean something. It would make the silence more specific. It would show that even among carefully chosen possible Earths, life leaves no easy mark. Soon, the question may shift from how many possible Earths exist to whether any of them are breathing. That future search brings tonight's journey back to the beginning. More than 6,000 confirmed planets now sit in our catalogues. Each one is a real world orbiting another star. Some were found as tiny shadows crossing distant suns. Some were found through the faint wobble of starlight. Some are giant planets heated by close orbits. Others are small enough to make us pause. Kepler turned those discoveries into statistics. It watched one patch of the Milky Way and showed that planets are part of the normal structure of stars. From that small window, astronomers learned to estimate the hidden population. The galaxy likely holds far more worlds than our telescopes can directly confirm. That changed the meaning of Earth. Earth no longer sits in a universe where planets are rare. It sits in a universe where planets seem almost expected. The harder question is what kind of planets they are. A habitable zone world receives the right amount of starlight for liquid water to be possible. That phrase sounds gentle. It carries the image of oceans and clouds. But the habitable zone only measures the relationship between a star's brightness and a planet's orbit. It does not tell us whether the planet has air. It does not tell us whether its water is liquid on the surface, buried under ice, trapped as vapor, or long gone. It points to a place where the deeper test begins. Proxima b showed that clearly. The closest known possible Earth-like planet orbits the nearest star beyond the Sun. It is only about 4.2 light-years away, close enough to feel almost intimate in cosmic terms. Its orbit lasts about 11.2 days. It sits near a small red dwarf that can flare and throw charged particles into space. It may have kept an atmosphere. It may have lost one. The nearest, almost Earth still has no clear face. TRAPPIST-1 made the mystery larger. One small star, about 40 light-years away, holds 7 Earth-sized planets. All 7 orbit inside the distance where Mercury circles the Sun in our own solar system. Several sit where surface temperatures could be interesting, depending on atmosphere and history. Then Webb began testing those hopes. For TRAPPIST-1c, the evidence ruled out a thick carbon dioxide atmosphere like Venus has. A world can match Earth in size and still fail the atmospheric test. K218b widened the picture again. It has methane and carbon dioxide in its atmosphere. It may be a hydrogen-rich world with an ocean beneath. It may belong closer to the strange class of sub-Neptunes. It is a habitable zone planet with interesting chemistry, yet it does not fit the simple image of a second Earth. That is the pattern. Every promising world becomes more complicated under better measurement. Size becomes density. Orbit becomes climate. Water becomes pressure. Atmosphere becomes chemistry. Chemistry becomes interpretation. Somewhere inside all of that, life may be waiting, or the universe may be full of places that came close. The Fermi paradox gives that uncertainty its deeper weight. If planets are common, and if possible Earths are common, then the silence becomes harder to carry. The sky has given us no confirmed biosphere beyond this one. No unmistakable living atmosphere. No verified signal from another civilization. No clear sign that another world looked back. The rare Earth hypothesis offers one path through the silence. Many rocky planets may exist, while the full Earth recipe may be much harder to repeat. The Great Filter offers a darker path. Life may begin and then stall. Microbes may flourish without becoming forests. Complex animals may appear without intelligence. Technology may arrive only briefly, then vanish before it spreads between stars. Future telescopes may begin to separate these possibilities. The Habitable Worlds Observatory is being designed to directly image nearby potentially habitable planets and search their atmospheres for biosignatures. Oxygen, methane, ozone, water vapor, and carbon dioxide may become the clues. A faint spectrum may someday carry the first evidence that Earth is biologically unalone. A long search with no living chemistry would also speak. It would make the silence sharper. So the meaning of 1,000 possible Earths is not simple comfort. It is a quieter kind of fear. Earth may be ordinary in shape. It may be one rocky planet among a vast number of rocky planets. But as far as we know tonight, it is still the only confirmed living world. One planet where oceans stayed. One planet where chemistry crossed into cells. One planet where life changed the air, filled the water, covered the land, and eventually built instruments sensitive enough to search the dark for another example. Somewhere out there, other mirrors may exist. They may be blue, frozen, airless, ocean-covered, or alive in ways we have not learned to recognize. For now, each one remains hidden behind distance and starlight, and Earth remains the only answer we can hold clearly.